Hey good people, welcome back. In this video we're going to discuss the types of errors that can occur when hypothesis testing. There are two types and we're going to investigate each type in this video by doing an example of each. Type 1 errors are sometimes called a false positive, and type 2 errors are sometimes referred to as a false negative. And I'm going to describe in greater detail what is meant by that. But I highly encourage that you read these pages in the textbook. There's a lot of vocab in this chapter that's new. The type 1 and type 2 errors, the power of a test, the effect size, the alpha level and the beta level. All of this is really conceptual and very important, and it'll be much easier for you to understand if you read these pages that I highlighted there. Alright, so a type 1 error is when you incorrectly reject a true null hypothesis. A type 2 error occurs when you incorrectly accept a false null hypothesis. Let's take a look at an example. I tried to make a nice example for a type 1 error that's actually somewhat tangible. I found an interactive deck of cards online, and we're going to be looking at that deck of cards. So let's read this very closely. Suppose there is a stack of 208 playing cards that is supposed to contain an equal number of red and black cards. This stack of playing cards was apparently created by combining 4 standard decks of playing cards. We suspect that there may not be an equal number of red and black playing cards in the deck. So we take a random sample of 20 playing cards and conduct a hypothesis test. So in this example, we have access to a stack of 208 playing cards, and we want to test if there's an equal number of red and black cards. So we're going to set our null hypothesis as it is a normal deck of cards. Let's let P equal the proportion of cards in the deck that are red. In a normal deck of cards, the proportion of red cards should be 50%. And if the deck is not normal, that's our alternative hypothesis, then the proportion of red cards is not equal to 50%. So we have our null and our alternative hypotheses. So here is my interactive deck of cards. You can see here, you could shuffle this deck of cards. There's all types of cards in there. I'm going to flip them over. Alright, so I have it here. I started dealing out my deck of cards already. I need to deal out a few more. Here we go. Now we have 20 cards dealt from 208, and the reason I made it out of 208 cards is because I didn't want to sample too few cards and I didn't want to sample too many. So 10% of 208 is 20.8, so we didn't go over the 10% rule, and we should expect to see at least 10 red cards and at least 10 black cards in a sample of 20. Alright, so let's flip these cards over. Alright, we have a lot of black cards so far. Alright, a couple red. Alright, so it looks like out of our 20 cards, there was only 5 that were red. I'm going to copy this over to my flip chart so I can work with it better. Let's write this right in here. Alrighty, so we have if P is the proportion of red cards, then our P hat is 25%. There's 5 red cards out of 20, and that's 25%. Again, our null hypothesis was that the proportion of red cards is equal to 50%, and our alternative hypothesis was that the proportion of red cards is not 50%, it's something else. We're going to conduct a hypothesis test. So what we do is we build a normal model, and we center our normal model around our null hypothesis. Our null hypothesis was that there was 50% of them should be red, and then we count 3 standard deviations in each direction based off our standard deviation formula for estimating P hat, and that is P times Q over N. and then we're going to plot our p hat on there and calculate the p-value. I took the liberty of doing that ahead of time, and I'm just going to paste that model in here right now. Here we go. So when I built this model, my standard deviation was 0.112. Calculate that again just to show you. So 50% red times 50% black out of 20 card sample, and I have a standard deviation of 0.112. I counted that standard deviation 3 times in each direction, and I plotted my p hat. Now, since this is a two-sided hypothesis test, we should also plot an equal number of standard deviations above the mean going this way. I think it was around 2.24 standard deviations below the mean, that p hat. So I'm going to go 2.24 standard deviations above the mean. All right. And what we do is we calculate the area underneath the curve from p hat to the left and from this number of standard deviations above the mean to the right. And that's our p-value. So the p-value is the probability of obtaining a sample proportion this rare, or even more rare, in either direction from the mean. And I like to use the normal CDF to do that, so I'm going to go second distribution, normal CDF, and I have it already set up. My lower bound over here is negative infinity. My upper bound is that cutoff value at p hat, which was 0.25. The mean of this probability model was 50%, and our standard deviation was 0.112. Now, once we get the answer, it's going to give us the area of the left curve. I'm just going to multiply that by 2 to get the area of both of them. And then we have our p-value. So our p-value is 0.026 if we round it. Our p-value is 0.026, which is about 2.6%. And that means that there's a pretty good chance that this is not a normal deck of cards. We usually set our significance level for making our decision at 5%. If there's less than a 5% chance of this happening due to random chance, then we can say it's probably not due to random chance. So because this is lower than 5%, we're going to actually reject our null hypothesis. So we reject the null, and we conclude that it is the proportion of red cards is not 5%. Because p-value is less than 5%. All right, so what we did here was we built a normal model based on the regular deck of cards that has 50% of them red. We plotted our sample proportion of red cards on that normal model, and we calculated the p-value, which was the probability of obtaining a sample result that far from the mean or further in the other direction. And we found out that that was a pretty low probability of occurring, so we rejected the null hypothesis. It's probably not a standard deck of cards with 50% red. Well, there's a problem. Sometimes we accidentally reject a true null hypothesis, and it turns out that that's what happened in this case. If you look at our deck of cards here, if I flip them over, if we were to actually count these out, there was a lot more red ones still to be found. It turns out this was a completely fair deck of cards with an equal number of red and black. So we actually ended up at the wrong conclusion by accident. And what that's called is an error. It's called a type 1 error in this case. This is the type 1 error because we incorrectly rejected a true null hypothesis. In fact, this was a fair deck of cards with an equal proportion of red and black cards. We erroneously came to the conclusion that it is unfair and there's more red cards. So we rejected our null when we really shouldn't have rejected it. Now, had we set our p-value threshold lower than 5%, maybe we set it at 1%, we would not have rejected our null hypothesis. So that's something the book talks about. 5% is very typically what they set as the benchmark for statistical significance, but you should be careful not to do what's called p-hacking, which is setting your p-value after you perform your experiment. The p-value that enables you to make your decision, that thing is called the alpha level. It's typically set at 5%. You could set alpha at 1% or anything else really, 10%. You could set it at 0.1%. But it's important to set that before you conduct your experiment. There's a nice little comic strip on page, I think, let's see here. It's on page 529 of the textbook. They explore the dangers in p-values and type 1 errors in this comic. I think it's something you'll get a kick out of if you read it carefully. It's a pretty funny comic strip, so that's on page 529. All right, so just to summarize, the reason we made a type 1 error is we rejected the null hypothesis when it was actually true. The null hypothesis was true. There is 50% red, but we rejected that because we ended up with a p-value that was lower than 5%. All right, we're going to go ahead and do another example now. This example is from the teacher's edition of the textbook. It's just a more straightforward problem. They just want us to read the scenario and identify the type of error that's being made. Suppose that a manufacturer is testing one of its machines to make sure that the machine is producing more than 97% good parts. Their null hypothesis is that the machine is producing good parts 97% of the time, and their alternative hypothesis is that it's producing good parts more than 97% of the time. The test results in a p-value of 0.122. Unknown to the manufacturer, the machine is actually producing 99% good parts. What probably happens as a result of the testing? So in this scenario, the manufacturer wants to check to see if the machine is producing more than 97% good parts. So they set their null hypothesis at 97%. They say that their null hypothesis is that it's only producing good parts 97% of the time. Their alternative hypothesis is that it's producing good parts more than 97% of the time. And they do a hypothesis test. They must randomly sample some parts, and they calculate a p-value equal to 0.122. Now, unbeknownst to them, the rate at which the machine is producing good parts is actually 99% of the time. But their p-value was 0.122. That p-value is not lower than the typical threshold for statistical significance, which is 5% or 0.05. So in this situation, given that p-value, they would not have enough evidence to reject the null hypothesis. So because they would not reject the null hypothesis, they would accept it to still be true. They would continue to believe that the machine is producing good parts 97% of the time. So whenever you fail to reject a false null hypothesis, you're making a specific type of error. And the two types of errors are type 1 and type 2. I'm going to paste the definitions in here. A type 1 and type 2 error. Here we are. So in this situation, are they making a type 1 or a type 2 error? They incorrectly accepted the false null hypothesis. They're going to continue to believe that the machine is producing good parts 97% of the time, and that is a type 2 error. So the answer to this is E. They failed to reject the null hypothesis, making a type 2 error. So it turns out that the real true rate at which they're producing good parts is 99%, which is higher than 97%. But their hypothesis test failed to realize this, and they failed to reject the null. They accepted a false null hypothesis, and that's called a type 2 error. All right, let's look at another example. In this next example, we just have to read a scenario and think about possibilities of type 1 and type 2 errors. So we're just reading this scenario and thinking about what a type 1 and type 2 error would mean in the context of this situation. A new cancer drug is being developed. The current success rate of treating a certain type of tumor with radiation alone is 60%. The drug is supposed to improve the success rate, and it has no side effects. So in this scenario, we have a typical success rate of treating a type of tumor is 60% of the time they're successful. There's a new drug being developed, and it claims to improve that success rate. Read the scenario, write the null and alternative hypotheses, interpret the meaning of both a type 1 and type 2 error in the context of this problem situation. So our null hypothesis would be that they're successful at treating the tumor 60% of the time. And the alternative hypothesis would be that with the advent of this new drug, they're actually successful more often than 60% of the time. What are some errors that could arise? Well, a type 1 error is incorrectly rejecting a true null hypothesis. What does that mean in the context of this situation? If they were to incorrectly reject the null hypothesis, they would say this is not true, when in actuality it is true. They'd be saying that the drug is effective at improving the success rate of treatment, when in actuality it's still 60%. So the consequences of committing a type 1 error in this case are probably pretty severe. They're now saying they have a drug that's effective at improving the rate of success at treating a tumor, when in actuality the drug makes no difference. It does not improve it. So that's a serious fault. A type 2 error would be incorrectly accepting a false null hypothesis. If they believed that this is true and they accepted this to be true, when in actuality this is true, they'd be committing a serious error there too. They'd be ignoring a drug that possibly works. They're thinking that it's true, that the null hypothesis is true when they commit this type of error. They're assuming that the rate at which the drug affects the success rate, it still stays at 60%. When in actuality, if they're committing a type 2 error, this is not true. The drug's actually effective at improving the rate. So if they committed this type of error, they would probably not use this drug, even though it is successful at improving the success rate at treating this tumor. So I wrote this out in a little bit more descriptive. Here are the situations that can arise. If they commit a type 1 error, the success rate really still is 60%, but we erroneously conclude that the drug is effective in increasing the success rate. That's a type 1 error. That's a false positive. Type 2 error, false negative. We fail to realize that the drug is effective. We erroneously conclude that the success rate remains 60% when it is actually improved. Alright, what I'd like you to do after watching this video is just to read those pages in the textbook that I uploaded along with this video. And we're going to have a meeting next week. There will be one more assignment assigned on Tuesday, and that will be the last one for this year. It's related to Chapter 20. It's related to types of errors. I'm going to try to make it multiple choice for you to make it a little bit easier. It's a lot of vocab in this chapter, so I really would like you to read those pages to get a better handle on the vocabulary. Thank you for watching and have a great Memorial Day.